Last lecture of this unit is on celestial sphere and the seasons. The celestial sphere is not a real object. It's a way of thinking about how the sky is in relation to the way that we see it. So the best way to think about the celestial sphere is that there's an Earth, and outside of it is this grid system for measuring and identifying where things are. For centuries, they thought that it was actually a real thing, that there was this sphere around the Earth, and some cultures have said that there were stars. The stars were actually holes poked in it and heaven's light shining through. Got really intricate. I like this one. This is like a little antique desk one that I imagine you can turn, grab one of the planets and move it around, and they'll all move supposedly at the right time. They got really intricate. This one is in a museum in Italy, I believe, and it was... look up if it's interesting to you, look it up on the Wikipedia page. They talk about how some of the wood in it, so this is 400 years old, wood, 500? 400? Yeah, whatever. I'm not a history teacher. I know it's simple, but I'm thinking astronomy right now. They've covered the they've covered the wood in gold and things like that, so kind of neat. When we're talking about the celestial sphere, there are some parts that you need to know. Basically, the vocabulary of this unit. North, south, east, and west is just the stuff that you know, the North Pole, South Pole. But we have a North celestial pole and a South celestial pole, and we have a celestial equator. These are all directly above the Earth. So if I go back to that original picture, the sphere around the Earth, that just simply matches with the stuff on Earth. There's some terms that you probably haven't heard of before, like one called the zenith, which is directly overhead the observer. Zenith was a TV manufacturer in the United States. I don't know if they're still around. I do know they were the last TV manufacturer in the United States. That was a while ago. Lots and lots of products named after astronomical terms, but not this one. Nobody would want, our product is the absolute lowest you can go. Buy the nadir, whatever, I don't know. Okay, so if you think about the sky, now I know that I'm being wrong, I know this is terrible, but if you think about the sky moving around the Earth, and you're going, Lanham, we've already been through that. That's called geocentric. Don't be an idiot. You go in your backyard and it doesn't feel like you're moving. It looks like the sky is moving. And that's actually the way that we've measured things. We still talk about the sun rising in the east. No, it doesn't. You are hurtling toward the sun on a ball of dirt at 900 miles an hour straight at this burning ball of fire. Okay, it's not fire. It's incandescent mass. But you get the idea. We're the ones moving, but we still talk about everything else as if it's moving and not us. So that's kind of what you want to picture in mind. When you do this, when you start paying attention, and we're a modern society that doesn't pay attention to this stuff. Last night, the night before, the moon looked really full, really pretty. It's not. If you looked at this every single day of your life and you depended on it, you would notice these little tiny things like, oh hey, there's some stars that never set. There's a constellation called Cassiopeia that's kind of like this up in the northern part of the sky that makes a little W shape. It never ever sets. You can't see it in the daytime, but it never sets. As you watch it all year, you can see the different parts of the sky, and then it's real obvious that thing never sets. What if you were to go to Alaska? Where would those stars be? So picture our little person walking north on our globe. Yes, there's a person right there. Those stars would get more and more overhead. There would be more stars that don't set. In fact, during the summer season, our star, our sun, never sets high enough up closer to the North Pole. And in the winter, it never rises. between there's times where the sun skims the horizon all the way around it, and that's your daytime and nighttime. It's cool stuff. You go down to Mexico, and there are fewer stars that never set. If you're on the equator, you would see the North Star, or right on the horizon. It'd be really hard to see. There actually is not a there's not a star at the South Polar, South Celestial Pole. I knew it's 3 words. I know how it is. But if you're on the equator, none of the stars would appear to set. And that gives you a really cool effect called star trails. And I like to do this with these pictures. This is the North Celestial Pole. So it's where everything seems to orbit around it. It's where the motion seems to go. And I'm looking at this little star trail, and it looks like a 90-degree thing. So this photographer put their camera on a tripod and let the Earth go 1/4 of the way around while they left their shutter open. 1/4 of one trip around is 24 hours, so 1/4 of that is 6 hours. So this photographer left his camera shutter open for about 6 hours to get this picture. And those are called star trails. I'm not going to edit that. I've already done this twice because I forgot to hit record before, so I'm just going to keep going. The celestial equator, just like our normal poles, is exactly between it, but let me introduce, there's something called the ecliptic. The ecliptic is where the sun traces a path across the sky. If you set up a video camera and video the sun all day and then run it at high speed, you'll notice it makes an arc across the sky. It's not a straight line, it's an arc. And that's actually kind of cool. All of the planets and the moon, everything, follow the ecliptic within a few degrees. Sometimes the ecliptic is higher in the sky and lower and so on, depending on the seasons. I already talked about the positions of those. They're directly above that. Like the North Celestial Pole is directly above the North Pole and so on. Astronomers really want to measure, and this is what Tycho Brahe did. They want to measure exactly where things are, so they use what's called right ascension and declination. Right ascension, you're just measuring how far east and west something is, and declination is how far north and south. So if you use a telescope that has what's called an equatorial mount, you can see that telescope kind of does this twisting motion because you point the telescope directly at the North Celestial Pole, and then you do declination. You kind of aim it south, and then you move along the right ascension, and it follows that star, the planet, whatever in the sky. You don't have to adjust left, right, up, down. You just go left to right, or basically forwards. You just make the telescope keep following it. So once you've learned to use that type of mount on a telescope, it looks complicated. It's complicated to get started with, but then it becomes really easy to use. The other type of mount is, what you might picture like, mounting a gun or something. If you've gone to Cactus Car Wash, they have the little thing where you can shoot the car and you point it up, down, left, and right. There's nothing fancy about it. You're going, that's what I want. Yeah, but when you're trying to track a star and you have to move, up and to the right, whereas this other one, you just move to the right, tracks things so much easier. It's kind of cool stuff. Okay, so if you'll take a look, this little plane, this disk here, represents the horizon or the celestial equator. And this one, though, is tilted. This is the ecliptic. Okay? So what we have is the sun travels round and around and around the ecliptic. So maybe every day at noon or something, it progresses a little bit further, and then at some point the sun crosses that celestial equator. That's our autumnal equinox. So that's the equinox that we just had last week. And now the sun drops below the celestial equator, which is still visible. The celestial equator is visible from us. And I think I accidentally said celestial equator represents the horizon. No, that's the line directly above our equator. So eventually the sun is going to drop very, very low in the sky, and the absolute lowest it goes is the winter solstice, which is usually around December 22nd, 23rd. The sun will not spend much time in the sky, so it's the longest night of the year. And then eventually we end up, there's the spring equinox, and then with the summer solstice summer solstice right there. So the equinox is when the sun happens to be crossing that celestial equator, and that's going to happen once a year. The solstice are the furthest spots from that.
Hi guys, Mrs. Polumbo here. I just wanted to talk to you about the celestial sphere. You've read about it in the content, and I just wanted to show you a real one here. So remember that a celestial sphere is a tool that astronomers use to kind of help them map sky objects in terms of where they're located. Just like we use latitude and longitude to mark locations of cities, we can use declination and right ascension to mark locations of stars in our night sky. So just to make sure you understand the key points, if we take the Earth's equator and extend it out towards the sky, we end up with the celestial equator, and I'm running my finger along that right here. Everything above the celestial equator makes up our northern sky. Anything below the celestial equator makes up our southern sky. A few vocabulary words that you need to know. As I mentioned already, declination and right ascension. These are two measurements that astronomers use to describe the location of stars. Let's start with declination. Okay, think of declination like your latitude lines. And so like latitude measures north and south of the equator. Declination does the same thing, but instead of saying north and south, astronomers use positive signs for anything in the northern sky and negative signs for anything in the southern sky. A key point that I want you to be aware of, when looking for Polaris, for people in the north, the height of Polaris, which is the North Star, the height of that star above our horizon is equal to our latitude. This means that for us in London, Ontario, its latitude is about 43 degrees north. So when looking for Polaris, you should be looking 43 degrees above the horizon. Okay, that will help you tremendously in trying to locate Polaris. Polaris, of course, sits directly above the North Pole, and I forgot to mention, if we take the Earth's geographical North Pole and extend it upwards towards the celestial sphere, it actually hits a star called the North Star, also known as Polaris. If we do the same for the South Pole, it does not hit any star in particular, okay? The other term, right ascension. So, right ascension is like your longitude lines. And the 0 point for longitude is the prime meridian, which passes through Greenwich, England. The 0 point for right ascension happens to be the vernal equinox, which is our spring equinox. And so that's where the sun crosses the celestial equator, okay? In terms of measuring right ascension, astronomers do so in time units. So the distance between each longitude line is about 15 degrees, and that's how much Earth rotates in an hour. Understanding that Earth completes one spin in 24 hours, and each spin is 360 degrees, mathematically that works out to 15 degrees per hour. So if a star is located 2 hours, if its right ascension is 2 hours, that means 30 degrees in longitude language. Okay, I think that's it. If you have any questions or concerns, please email me. I'm also going to come on and talk to you about the Hertzsprung-Russell diagram, and so I'll deconstruct that for you and talk about all the stellar properties that we use in looking at the Hertzsprung-Russell diagram. Take care. Bye.
Okay, this is neat. If you set up your camera and take a picture every day for a year, do it at the same time. This one happens to be at noon above Stonehenge. You get this shape. It's called an anemone, a lemon, one of those. And so the tips of this would be the solstice, where the sun is the highest and the lowest in the sky, and the intersection would be the equinox. Stonehenge specifically, and no, I don't know which stone, but one of these stones, all the stones have names. You can see that this lines up nicely, and right here at the equinox, this thing is set up so that two of the stones line up properly and point directly to the equinox. So in other words, the sun rises the day of the equinox exactly over a certain stone. So every year, been doing that for thousands of years. Okay, when I talk about altitude of the sun, I'm not talking about how far away it is from Earth. I'm talking about how high it is in the sky. In the winter, it is very low in the sky. So we would say it's further south. Unless you're Australian, then we got the opposite going on here. Because if you go south in Australia, you're heading toward the beaches. It's, their Florida kind of thing. In the summer, the sun is rising higher and higher. It does not go directly overhead for us, but also check out the shape. It really rises very, very north and sets very, very west. So it does this arc across there. And there's all sorts of implications of that. One of them is kind of neat. There was an architect, Frank Lloyd Wright, and if you think of the sun shining from those locations to that person like this, Frank Lloyd Wright built a house. This is my Frank Lloyd Wright building. If you know who I'm talking about, you're laughing. And in the winter time, the sun would shine through the windows and heat up the house, but that overhang would catch the sunlight during the summer and would keep the house cool during the summer. His homes built this way don't really use heating and air conditioning as much as a modern home. Of course, he incorporates lots of stone and things like that to trap the heat and regulate it and everything, but that's a pretty common architectural tidbit. So during the winter, check this out. All right, I've got my drawings in there. Let's try and clear those up. In the summer, the sun doesn't spend very much time in the sky. So not only is it a different angle, but there's a different amount of time spent in the sky, which is what lends us our seasons, or one of the main things that lends us our seasons. The other is, if you shine a light and you're only looking at this small little area, so in other words, the width of this sunbeam is the same as the width of this sunbeam, and they make different areas on the surface of the Earth because the surface right there is tilted. If I did it up here at the pole, it would be much more exaggerated. So you have what's called less energy density. There's less sunlight per area striking the ground when the ground is slanted away from the sun. Here on the closer to the equator, actually that's Florida, but that's closer to 90 degrees relative to the ground. 90 degrees here, 90 degrees there. You can see that, each of these being up, the difference of sunlight hits at a different angle, and as at a greater angle, it's going to spread out a lot more. The seasons are caused by the tilt, which allows the sun to be in the sky a certain amount of time, or the sunlight to be spread out on the ground. Combine those together, and that's why we have our seasons. Some people say the seasons are because we're closer to the sun, further away from the sun. We are actually closest to the sun in our orbit on January 4th, in the middle of our winter. The distance between Earth and the sun varies, but not that much. It barely affects the temperature planet-wide, so kind of cool. I have to put that in there. I always like that geeky stuff there.
In the Northern Hemisphere, December has the fewest hours of daylight and the most darkness, because at that time the tilt of the Earth's axis is pointing the Northern Hemisphere away from the sun. However, as counterintuitive as it might sound, December actually has the longest days of the year. Modern clocks, of course, think every day is 86,400 seconds long, but that's just the average length of a solar day over the course of the year. A solar day is what you actually measure with a sundial, or equivalently, it's the time it takes for a line of longitude on the Earth to rotate back to face the sun again. This actually requires slightly more than 360 degrees of rotation because the Earth isn't just sitting in space rotating. It's also moving around the sun, so it has to rotate roughly 361 degrees before the sun comes back perfectly overhead a particular place on consecutive days. If the Earth's orbit were perfectly circular and its axis were perfectly upright, that would be the end of the story. However, the Earth's orbit is elliptical, so sometimes the Earth is slightly closer to the sun, and the peculiarities of gravity mean it moves faster when it's closer to the sun, so it goes farther around the sun in 24 hours. So the Earth has to rotate slightly farther before the sun comes back right overhead. 0.033 degrees farther, to be precise. More rotation takes more time, so when the Earth is closest to the sun, the real sundial measured day length is lengthened by about 8 seconds. Plus, the Earth's axis is tilted, which is what gives rise to the seasons, but also means that at the time of year when the tilt points towards or away from the sun, narrower slices of longitude are aimed directly at the sun. So as the Earth moves in its orbit, it has to rotate slightly farther in order for a particular line of longitude to catch up with the changing direction to the sun. 0.088 degrees farther, to be precise. And again, more rotation takes more time, so when the Earth is tilted towards the sun, the real sundial measured day length is lengthened by about 21 seconds. Now, by a strange coincidence, we live during a time in geologic history when the Earth's closest approach to the sun happens almost perfectly to coincide with one of the two times of year when the Earth's tilt is oriented directly towards the sun. So these two day lengthening effects add up, and on December 22nd, the length of a solar day as measured by a sundial will be the longest it is all year, 86,430 seconds, for a grand total of 30 extra seconds. Oh, and in case you're wondering where those 30 extra seconds on December 22nd go, well, they get pushed into December 23rd, and the extra seconds from the 23rd get pushed into the 24th, and so on, which is why solar noon, or the time that the sun is directly overhead, shifts about 30 seconds later every day around the solstice. This increasing disparity between solar time and clock time is also why in the Northern Hemisphere, the earliest sunset happens a few weeks before the solstice, and the latest sunrise happens a few weeks after.
That video, they said that December 22nd is the longest day of the year, but the sun is the lowest. So what they're saying day is the 24-hour thing all the way around. Since the sun is lower in the sky, it's actually the longest night of the year, which is mentioned in Robert Frost's poem, A Walk in the Snowy Woods. So go check it out. Have a good day.